Okay, so I ran out of time on the last video, so wanted to make another one to show you some examples that are that have multi-features and more pertain to what we will be doing in class. And this specific example, we'll have to use the normal distribution function to solve for the posterior terms instead of the previous example at the end of the first video. Is we were able to find those values just by counting and eyeballing off of the graph. So this is a sex classification example. There's two classes, male and female. So we'll want to determine a test subject, whether they are male or female, based off of these three features. The three features are height, weight, and foot size in inches. So this is the training set, and we have 4 occurrences of male, 4 occurrences of female. So we use the training set to determine our mean and variance values. The average height for a man, 5.855. For a female, 5.4175. And these are the respective variances for both male and female. And these are the weight and variance for both for the weight of male, female, and also for the foot size of a male and a female. So now that we have this data based off our training set, we want to start running some test samples through this. Also, based off of the assumption that we're only looking for a man and a female, we could determine that the priori term is 0.5 for both the male and female. This is the naive part of the Bayes classification. We're assuming that we could only get a male and a female based off of these test samples. So there's not going to be a random sample of a cat image being run through this algorithm. It's we're just pretty much looking at human beings, and there's only 2 options. So here is our test sample. We don't know the sex, that's what we're trying to figure out. But the height of the person, 6 feet, weight is 130 pounds, and the foot size is 8 inches. So going back to the to this set right here of the Gaussian distributions of the mean and the variance, just by looking before we do the equations, run the equations through the normal distribution function, we could just kind of take a look at it and make a gut decision. The height is 6 feet, so if you look at the average heights, it's closer to the male value. However, the weight and the foot size for both of these, for the sample, is closer to the woman's average weight and the woman's average foot size. So one of these features says that it's likely to be a man, and the other 2 features say it's probably likely to be a woman. So your gut could kind of assume that it's probably a woman, but it's a tall woman. It's kind of an exception based off of this data. But so we'll want to run it through the equations that I showed you before to find the posterior term of the male, and that's the likelihood of it being a male given the features. So these 2 equations are very similar. The only thing that really is different is the male as opposed to female. So here is your to recap, your priori term and your 3 likelihood terms, and the evidence is in the denominator. Same thing here, priori, 3 likelihoods, and your evidence. And in this case, because the evidence term is scales both posteriors equally, it's kind of irrelevant. It's going to affect both equations the same, so it could be ignored in this. It won't affect the classification. So we already figured out what these 2 terms were, so now we have to figure out these 6 terms here, or these 3 and these 3, for a total of 6 terms. Then find the product of these numerators, and whichever value is the highest is what the class is the class that'll get assigned to this random test subject here. So in this case, because we have this data set here, this training set, and we figured out means and variances for each one, we're going to use the normal distribution function, and let me show you that. So here's the normal distribution function for a Gaussian naive Bayes. If you haven't seen the normal distribution function, here it is. It's pretty similar to if you took a probability class. Here is your mean term in the numerator of this exponential term, and here is your variance term that goes here and here. The only other unknown term here would be your v, and that represents the total number of features in your set or your algorithm or whatever test that you're using. So let me scroll back down to the example. So we're gonna first find the probability of height given that it's a male. So we're gonna use these two values for the mean of the height mean of a male and the height variance of a male. So here's the mean and the variance. So the variance goes here and here. The mean goes here. The reason why this is 6 is because there's 6 different types of features, or there's 3 features, but there's 3 for each, the male and the female. So there's 6 here. That's why we use 6. So when you run it, do the calculation for the normal distribution, you get this value here. So we have this value and this value. We need to find the weight and the foot size likelihoods. So again, you use the respective mean and variance according to the male height and the male foot size, and you get these values. So now we have all the terms in our numerator, and we want to find the product of all 4 terms, and that'll be the posterior for that specific sample being male. And when we multiply those 4 values out, we get this term right here, or we get this value here. Now we also want to do it for the female. So using the respective means and variance values for each feature according to the female results, we get these 4 values, which is all in the numerator. Multiply those all out, and we get this value. So you can see clearly that the posterior value for the female is higher than this value here for the male. So when this sample goes through your algorithm, it's going to be generated as a female class. So this person will be classified as female, which matches pretty close to the weight and the foot size. But this female just happens to be taller. Here's another multi-feature example using the naive Bayes model. In this case now we have 14 different occurrences with 4 features, and the class in this case is going to be a yes play or a no play. So you're using this data to determine whether the predictability of a play condition. So I'm assuming it's some type of a sporting event, whether the sporting event can be played or not given 4 different features of weather data. So I'll run through this one a little bit more quickly here. So when you break all this data here of these 14 occurrences, you get these results here. So you have your outlook feature, temperature feature, humidity feature, and wind feature. When you break all the data down, you get 2 yeses for sunny, 3 no's, and etc. for all these other values. The ratio is 2 of 9 because the sums of the yes equals 9 and the sums of the no is 5, and coincidentally it just works out for all the other features. So you get 2 out of 9, 4 out of 9, 3 out of 9, 3 out of 5, 2 out of 5. And for the plays, it's 9 out of 14 and 5 out of 14 because there's 14 different pieces of data. So now we have this, we used our training set and we have some of our values, and now we want to determine, based off of this sample of the 4 feature types, can the sporting event be played or not? What's the probability of it, of the event being able to get play all the way through or having it be canceled? So we want to find the probability of yes, given that E occurs. So we need to find the products of the outlook being sunny, yes, the temperature being cold, yes, and humidity being high, given yes, and the event of it being windy, given yes. So we use these values up here, these ratios, and we substitute all these, and we get this numerator up here. And this explains why we don't need to use that denominator, the evidence term. We ignore it because it's only relative compared to the other values, compared to values of other classes. Here they did it a little differently as opposed to the last example. When you multiply those terms out for the s, you get this value. When you multiply it out and find the posterior for the no's, you get this value. So you could see from these two values that it's going to be classified that no, you can't play the game given these 4 conditions. Even though it's sunny, but the temperature is colder, with high humidity and high wind, it's going to be classified that the weather is not going to allow for the game to be played. They actually go and convert this data right here into a probability by normalization, which means they just determine the yes on the and divide it by the probability of yes and no. So it's the same. It's the same result. The no is a higher value, so the no is what is classified given that example. Okay, one last example. This one's using text classification. So you're given a training set of 6 documents here, and these 6 features of the word kill, bomb, kidnap, music, movie, and television. And these are the 2 classes. We want to classify these documents as either being in the terrorism class or the entertainment class. So we have our given data, and we build our naive Bayes model off of that. And I just want to skip down here. You guys have seen all this stuff before. So we have the test document, given a random sample, and we want to find the posterior probabilities for each class given this test document off of these 6 features and determine what the class is. So again, we're going to find the posterior for each class, and then the products of every feature given that class. And we don't have to worry about the evidence term, the term that's in the denominator, because it'll affect the classification in the same way, so it's not necessary. So here's the bulk of the problem. We want to figure out the probability of this test document being classified as terrorism, given that you have this test document. So here is your priori term, and here are your 6 likelihood terms of each feature: kill, bomb, kidnap, music, movie, and television, given the class terrorism. When you do the multiplication, you get this value for the posterior, and for the posterior of entertainment, given the test document, you get this value. So obviously this value here for the posterior of terrorism is higher, so the test document will be classified as a terrorist class. And it makes sense because if you look at the features, you had 2 words in the whole document: kill, 1 word was bomb, 2 words were kidnap, and out of the entertainment features, you only had 1, and it was television. So obviously you can kind of assume that it was going to be classified as a terrorist document.